Thank you for the introduction. Hello everyone, I'm Shoma from Alibaba Cloud. Today I will introduce our experience of deploying user space TCP in Alibaba Cloud Storage with Luna over the past 5 years. Here is the outline. First, let me introduce Luna Alibaba Cloud Storage and its network. Our cloud storage architecture adheres to a compute-to-storage disaggregation philosophy. The compute clusters and storage clusters are connected with the front-end network, while different services inside one storage cluster are connected with the back-end network. As you can see, network plays a very important role in the cloud storage. We first take elastic block storage as an example. In elastic block storage, users' write request from a virtual machine is first sent to the block agent in the compute mode. Then the request goes through the front-end network and reaches the block server, which maintains a volume-to-file mapping table as a middle layer. Finally, it goes to several chunk servers, the storage engine of our distributed file system, and persistently saved in the local disks. Other storage services like Object Store Service and Cloud Table Store Service also have similar architectures as EBS. The only difference is that the user requests to the front-end interface are from the internet. The backend network architecture usually follows a two-layer closed topology and is homogeneous, so we can optimize it with RDMA. However, the front-end network is quite different and has several challenges. Here are the requirements of the front-end network. First, the compute clusters are deployed in different ages and are equipped with different drivers and network cards. Besides, the network is supposed to support a large amount of connections and connect to different clusters from geographically far apart availability zones for the worst case. Moreover, there are engineering effort constraints. Back to 2017, due to the product release plan, we didn't have years of time to develop and deploy a new protocol at a large scale without any concerns. Actually, kernel TCP was always a good choice for the front-end network for its high reliability and compatibility. It can satisfy the requirements listed here. However, storage is one of the most performance-sensitive scenarios in the cloud. Performance matters a lot. We tested kernel TCP with our microbenchmark, which emulates a common RPC service in the data center as is shown in the diagram. The results show that the performance of kernel TCP is bad, way too far from the SLAs of our cloud storage products for both latency and throughput. That is because kernel TCP involves high overhead of interruptions, multiple memory copies, context switch, locks, and inter-cop competitions, so it's no longer suitable here. To solve the performance problem, there are two solutions, RDMA and the existing user space TCP solutions. We cannot use RDMA for the front-end network because some of our legacy machines didn't have RDMA-enabled NICs at that time. And the large amount of connections in one single machine will also decrease the performance of RDMA. As for the existing user space TCP, we found it not trivial to apply them directly. First, these systems still have performance issues like inter-call communication and memory copies, although much better than the kernel TCP. Second, these systems usually take over all traffic, so it's hard to cooperate with kernel TCP-based applications on the same machine. Finally, there are always more or less compatibility issues of these solutions on various hardware. So our choice is to design and implement a new user space TCP from scratch for our cloud storage. That is Luna. Now let's take a look at the designs of Luna. Here is the overall architecture of Luna. Luna is designed as a libOS with run-to-completion mode. That is, each application runs its own network stack and application logic runs along with network processing in the same thread. Although Luna shares many similar designs to other user space TCP solutions, such as using DPDK user space drivers and share nothing model, it indeed includes several specific stuff for the cloud storage. We divided it into 3 categories: the thread model, the memory model, and the traffic model. In the thread model, to get the best performance, especially for latency, we use a run-to-completion pattern to avoid context switch and improve the cache collectivity. There are 2 different run-to-completion models in Luna, namely batch R2C and inline R2C. For the batch R2C, Luna divides the request processing into stages and handles a batch of tasks at each stage. This is similar to MTCP and IX, but Luna finishes all the processing in the same thread. In contrast, for the inline R2C, Luna processes each packet to completion. Luna first receives a batch of packets from the NIC. If the packet contains a complete RPC request, Luna will evoke the previously registered callback function. Then the RPC response generated by the application logic will also immediately get processed at the network layer. Luna adds network headers and forwards the packet to the NIC. After that, Luna starts the next round in the same way. The batch R2C model can enable fast porting of applications written using the EPO framework to Luna, but it introduces overhead of event NQ and DQ. The inline R2C model removes unnecessary overhead, providing the best latency, but it requires the application to change the performance model. The programming model, Fortunately, we can hide the change using an RPC framework. Both of these 2 models may introduce a risk of thread harm when getting blocked by the application logic. This is acceptable in Alibaba Cloud storage because Luna's upper layer applications are co-designed, which limits the complexity of each RPC call and has a flow control to prevent traffic burst. Then let's check out the memory model. Luna provides a transparent full-stack zero-copy for applications. Upper applications can directly pass pointers to the content across different layers, just like using the memory allocated from the heap. This is supported by Luna's user space memory slab, ZBUF. The ZBUF memory pool is designed with careful memory address arrangement, which helps get the metadata from the buffer address. Finally, let's look at Luna's traffic model. Unlike other existing user space TCP solutions, which take over the entire NIC and manages their own control plane at user space, Luna collaborates with the kernel network stack and leaves the complex and error-prone control plane to the kernel. To achieve this, Luna leverages SRIOA or flow director technology. We set up some flow steering rules directing specific flows to the given receive queue of Luna and let the rest go to the kernel stack, including ARP or SMP packets. We then use the netlink socket to synchronize the information about the ARP or routing table with the kernel. In this way, different applications using Luna and kernel TCP can run on the same machine without interference. Then let's take a brief look at the performance evaluation. We tested Luna, a Linux kernel TCP, and other user-space TCP implementations using our benchmark, which is described in previous thread. And the experimental results show that compared with Linux kernel network stack, Luna could reduce tail response latency by 70% and increase throughput by 3.5 times. And Luna also outperforms other existing user space TCP solutions, including MTCP and VPP. We also collected performance data in the production environment, since Luna has already been deployed in production for several years. For elastic block storage, Luna can help increase throughput by 50% while maintaining the latency. For table store service, end-to-end latency has dropped by 50% to 68% under the same workload. Okay, in the following part, I will share some lessons and design choices of Luna. Let's talk about the architectural design choices first. In general, the architectures of user space network stack can be mainly divided into 4 types: microkernel mode, sidecar mode, scheduling mode, and run to completion mode. Luna is designed with libOS and run to completion mode, running the network stack and application logic in the same thread. Another notable user space network stack is Snap, as it is widely deployed in Google's data centers. Snap uses a microkernel architecture with a dedicated process for network processing. Other applications running on the other cores communicate with Snap through shared memory, while Luna is designed and optimized for cloud storage, where performance is the most critical. So the overhead of context switch and intercall communications are not acceptable. In addition, Google implements Snap in a microkernel mode to support transparent upgrades. It also supports various services with different network characteristics. That is very amazing. However, Luna is customized for the specific application here, Alibaba Cloud storage. So the network stack is only updated with regular upgrades of the storage service, not so frequently. Therefore, the libOS model is more suitable here. We have noticed that several recent researchers announced that TCP is no longer suitable for data center network. So why do we still use TCP in Luna? First of all, it's compatible with kernel TCP-based legacy application, and applications can easily port it to Luna. Secondly, back to 2017, we could now put a huge effort into developing a new transport protocol and making it stable in all scenarios. Moreover, we found TCP is good enough for our storage service, especially for the 50 gigabit per second network at that time. We also tailored Luna TCP stack for better performance. For example, we implement a straightforward yet high-performance TCP fast path for the packets arriving in order, because out-of-order packets are not common in data center. As for congestion control, we found that just using neural is enough, because complex congestion control algorithms do not show significant improvements to our cloud storage from our experiment. And since data center network is homogeneous and predictable, we fix the RTO at a precision of several milliseconds, which greatly helps reduce the recovery time from network failures, which is very common. Finally, let's take a look at the network evolution of Alibaba Cloud storage. Before 2018, Alibaba Cloud storage was primarily built on top of Linux kernel. In 2018, after 9 months of developing and testing, Luna was deployed to Alibaba Cloud storage to support the highest performance storage product at that time. In this release, applications are programmed with a batch RTC model and use socket-like APIs, which still requires memory copies when sending data out. After then, Luna became the default transport layer for all the new servers of Alibaba Cloud storage. In 2019, we further optimized the performance by implementing a Luna customized RPC framework, which uses the inline RTC model and provides an I/O vector-oriented API for full stack zero copy. Since then, we have continuously optimized Luna to adapt to different storage scenarios. In 2020, we began to discover that TCP and software had their inherent limitations. So we began to we designed a new transport protocol called SOLA. More details can be found in our previous paper in SIGCOMM. The paper's name is From Luna to SOLA. Finally, let me make a brief conclusion. In this paper, we introduced Luna, a user space network stack designed and optimized for cloud storage, and share our experience during the past 5 years deployment in Alibaba Cloud. We introduced the network architecture of Alibaba Cloud storage and the constraints when designing Luna. We point out 3 important design pieces, namely threat model, memory model, and traffic model. And in the end, are the discussion and lessons learned from our experience. That's all of my presentation today. Thanks for listening.